In the summer of 2022, a telescope with a mirror built from 18 hexagonal gold-plated segments opened its eye for the first time and looked back across nearly the entire span of the universe. What it found waiting there was not what anyone had prepared for. Galaxies existed in the first few 100 million years of cosmic history, bright, structured, and in some cases already carrying the chemical signatures of stars that had lived and died. By the numbers astronomers had trusted for decades, very little of this should have been possible yet. Picture the scene, for a moment, the way it actually unfolded. Not a dramatic announcement delivered from a podium, but a quiet stream of data arriving at research computers scattered across the world, downloaded, processed, and studied by scientists who had spent years preparing for exactly this moment, and still found themselves unprepared for what the numbers actually showed. Somewhere in that data, hidden among thousands of ordinary points of light, sat a small number of galaxies that simply should not have been there yet, bright, orderly, chemically developed. Sitting in a period of cosmic history the models had reserved for something far younger and far less formed. That is the shape of the mystery this documentary follows. Not one startling image, but a pattern of results that kept arriving, year after year, each one a little harder to explain than the last. Why did the James Webb Space Telescope's galaxy discoveries leave so many scientists genuinely uncertain not about whether the data was real, but about whether the story of the universe's youth needed to be rewritten? Over the next several hours, we will follow that uncertainty from its first appearance in a handful of unusual points of light, through the specific galaxies that forced the issue into the open, to the competing explanations now being tested against one another. Some of those explanations leave the universe's age exactly where it has always been. Others do not. We will look at both, slowly, in the order the evidence itself arrived. Along the way, we will also look at how science has handled anomalies like this one before moments when careful observation ran ahead of existing theory, and the field had to decide, patiently, what to do about the gap. The unsettled feeling among astronomers did not come from a single image. It built slowly, discovery by discovery, each one adding weight to a question nobody had expected to be asking this soon. The standard model of cosmology, the framework that describes how the universe began, how it expanded, and how its first structures formed, had made fairly specific predictions about what the earliest galaxies should look like. They should be small. They should be faint, still gathering themselves out of primordial gas, still young in every sense the word can carry. For decades, no instrument existed that could actually check this prediction against the deepest part of the record. Webb was built, in part, to finally do that checking. What it found instead were galaxies bright enough, massive enough, and in some cases old enough in their internal chemistry that they should not have had time to exist, not according to a fringe theory. According to the same standard model that predicted their faintness in the first place. This is the kind of contradiction that does not resolve itself quietly. It sat, unclaimed, in front of thousands of researchers who had spent careers building their understanding of cosmic history on the assumption that this part of the story, at least, was settled. It was not settled. It still is not, entirely. And that uncertainty is the actual subject of what follows, not as a controversy to be sensationalized, but as a genuine and still unfolding scientific puzzle. Observe the way the record itself presents it. It is worth being precise, from the outset, about what this account is and is not. It is not a story about a telescope breaking physics, or about scientists secretly panicking behind closed doors while presenting false confidence to the public. Nothing observed contradicts a single confirmed law of physics. What it is, instead, is a story about the ordinary, unglamorous, genuinely difficult work of updating a model when new data does not fit it cleanly, work that is still underway, conducted by researchers who disagree with each other, in public, in the pages of peer-reviewed journals, about exactly how serious this particular anomaly turns out to be. First, though, It helps to understand what this telescope actually does and why an instrument built to observe infrared light became, almost by accident, a machine for looking directly into deep time. Light does not arrive instantly. It moves at a fixed, finite speed, which means that to look far away is also to look far back. A photograph of the moon shows the moon as it was a little over a second ago. A photograph of the sun shows the sun as it was 8 minutes ago. Stretch that principle far enough, across billions of light years instead of light minutes, and a telescope stops being a camera and becomes something closer to a record, a way of reading light that left its source before the Earth existed, before the sun existed, before almost anything familiar had taken shape. The James Webb Space Telescope was built to read that record at a depth no instrument had managed before. It does this by observing in infrared, a part of the spectrum invisible to human eyes but essential for a specific reason. As the universe expands, the light traveling through it stretches. A wave of visible light emitted by a very distant, very early galaxy does not arrive at Earth as visible light. By the time it crosses billions of years of cosmic expansion, that wave has stretched into the infrared. Astronomers call this stretching redshift, and the amount of redshift in a galaxy's light functions as a kind of timestamp. The more stretched the light, the older and more distant its source. Consider what this actually means for the light itself. A photon that begins its existence as part of a hot, blue-white burst of star formation, somewhere inside a galaxy still assembling itself out of primordial gas, spends the next 13 billion years crossing a universe that never stops expanding beneath it. With every passing eon, the space it moves through stretches a little further, and the photon's wavelength stretches along with it, blue sliding toward red, red sliding beyond what any human eye could register, until what finally strikes Webb's mirror bears almost no resemblance, in wavelength, to the light that first left its source. The information survives the crossing. Only its color changes, in a way precise enough that reading that color backward tells astronomers almost exactly how long the light has been traveling. This is why Webb was not built with a mirror or the instruments of a telescope meant to look at nearby stars. It was built specifically to catch this ancient, stretched light and to catch a great deal of it, using a primary mirror over 6 meters across more than 2.5 times the light-collecting area of the instrument that came before it, positioned nearly 1 million miles from Earth, shielded from the sun's heat by a 5-layer sun shield the size of a tennis court. The telescope was designed to do one thing better than anything humanity had built before: look back, as far and as clearly as physics allows. What no one fully anticipated was how much would be waiting there when it did. The James Webb Space Telescope launched on Christmas morning, 2021, from a spaceport on the northeastern coast of South America. It rode atop an Ariane 5 rocket, folded into a shape that bore little resemblance to what it would eventually become. The mirror was creased in on itself. The sun shield was compressed into a stack of fabric layers no thicker than a folded blanket. Almost nothing about the telescope in its launch configuration looked capable of the work it had been built to do. That was intentional. Nothing that large, the finished observatory, would span roughly the length of a tennis court could survive intact inside a rocket fairing. It had to fold, launch small, and then unfold itself across nearly 1 million miles of empty space, with no astronaut nearby to help if any part of the sequence failed. Over the following month, it did exactly that. Sunshield layers separated and tensioned, one at a time, each a fraction of the thickness of a human hair, spaced apart to form 5 separate barriers against the sun's heat. The secondary mirror boom extended. 18 hexagonal primary mirror segments, each coated in a microscopically thin layer of gold chosen for how efficiently it reflects infrared light, unfolded into their final honeycomb arrangement. More than 300 individual points of potential failure had to succeed, one after another, for the telescope to become operational. All of them did. By the end of January 2022, Webb had reached its destination, a gravitationally stable point called the second Lagrange point, or L2, located nearly 1,000,000 miles from Earth in the direction opposite the Sunday. At L2, the combined gravity of the Earth and Sun allows a spacecraft to maintain a stable position relative to both, orbiting the Sun in step with the Earth without needing constant course correction. It is also, conveniently, a location where the Earth, Moon, and Sun can all remain behind the sun shield at once, a necessary condition for an instrument that needs to stay extremely cold to function. Webb's infrared detectors operate best near absolute zero, some cooled actively to roughly 7 Kelvin, just a few degrees above the coldest temperature physically possible. Any stray warmth, including heat radiating from the telescope's own sun-facing side, would wash out the extraordinarily faint signals the instrument was designed to catch. The 5-layer sun shield handles most of this work passively, reducing the temperature difference between its sun-facing and space-facing sides from several hundred degrees down to a level the telescope's own hardware can manage, without requiring the enormous power draw active cooling across the whole structure would demand. This matters more than it might first appear, because the entire premise of the telescope depends on catching light that is almost unimaginably weak. A galaxy sitting near the edge of the observable universe does not announce itself. Its light has spent over 13 billion years spreading outward, growing fainter with every additional light year of distance, until what finally reaches Webb's mirror is a signal so faint that a warm instrument sitting nearby would simply drown it out. Webb was built cold, kept cold, and pointed carefully away from every heat source in the solar system, specifically so that this ancient, exhausted light would have a chance to be heard. Getting to that cold, stable configuration required what mission engineers, only half-jokingly, called 29 days of terror, the stretch of time between launch and the final confirmation that the telescope had reached its orbit and completed its deployment sequence successfully. Unlike the Hubble Space Telescope, which orbits close enough to Earth that astronauts could visit it for repairs and famously did in 1993 to correct a flawed mirror, Webb was placed nearly 1,000,000 miles away, far beyond the reach of any current human spaceflight capability. There would be no repair mission if something failed during deployment. Every hinge, every motor, every one of the more than 300 single-point failures had to work correctly the first time, unsupervised, with only automated systems and pre-programmed sequences to guide the process. Engineers who had spent decades of their careers on the project watched the deployment unfold in real time, from mission control, with no ability to intervene beyond sending commands and waiting to see whether they executed as planned. They did. Webb carries 4 primary scientific instruments, each suited to a different piece of this task. The near-infrared camera, or NIRCam, captures the wide-field images most people associate with the telescope, and it was NIRCam that first flagged many of the extreme redshift candidates through the dropout technique described earlier. The near-infrared spectrograph, NIR-SPEC, performs the more demanding work of splitting a candidate's light into its full spectrum, the step required to confirm a redshift with real precision rather than a photometric estimate alone. The instrument responsible for confirming both JADESGS Z140 and MOM Z14 beyond reasonable doubt. The mid-infrared instrument, MIRI, reaches even longer wavelengths, useful for studying dust and cooler material, though less central to the extreme redshift story than NIRCam and NIRSPEC. And the fine guidance sensor keeps the entire observatory precisely aimed, correcting for the smallest drifts and pointing across observations that sometimes last many hours, gathering photons one at a time from sources so faint that any instability in aim would blur the result beyond usefulness. And the reason astronomers wanted to hear it at all comes back to redshift, the stretching of light as the universe expands. Imagine a wave traveling across a piece of fabric, and then imagine that fabric being pulled outward from every direction at once. The wave stretches with it. Light behaves the same way as it crosses the expanding universe. A wavelength emitted as visible or ultraviolet light billions of years ago, by the time it reaches us, has been stretched into the infrared. The more distant and ancient the source, the more extreme the stretch. A galaxy from the universe's first few 100 million years does not merely appear dim. Its light has been shifted almost entirely out of the range human eyes can perceive, which is precisely why a telescope built for visible light, however powerful, could never have found it. Webb's instruments were built around this fact from the beginning, tuned to a range of infrared wavelengths specifically chosen to catch light from the earliest possible galaxies, the ones whose light had been stretched the furthest across the greatest span of cosmic time. There is a way to think about what this means that makes the scale easier to hold. Every additional unit of redshift corresponds to looking further back in time, not metaphorically, but literally, in the same way that opening an old photograph shows you a moment that no longer exists in the present. A redshift of 1 corresponds to roughly 8 billion years ago. A redshift of 6 or 7 reaches back to the era when the first galaxies were assembling out of the universe's early gas. Beyond that, into redshifts of 10, 12, 14, the telescope is looking at light from less than 500 million years after the Big Bang, a period astronomers call cosmic dawn, when the first stars were igniting and the first galaxies were only beginning to take shape. Before Webb, this era was effectively invisible. The Hubble Space Telescope, launched in 1990 and still an extraordinary instrument in its own right, could reach some distance into this territory, but its mirror and instruments were not tuned for the deepest infrared wavelengths where the earliest light resides. Hubble's deepest images showed galaxies from perhaps 600 or 700 million years after the Big Bang, faint smudges at the very edge of what the telescope could resolve. Cosmic dawn itself, the true beginning of galaxy formation, sat just beyond reach, a period astronomers could model and predict, but not directly observe. That changed on the 12th of July 2022, when the first full-color science images from the James Webb Space Telescope were released. One of them, a deep field image of a patch of sky no larger than a grain of sand held at arm's length, showed thousands of galaxies layered across billions of years of cosmic history in a single frame. It was, by any measure, an extraordinary technical achievement, the deepest, sharpest infrared image of the universe ever captured. But it was not the image itself that unsettled the field of cosmology. It was what astronomers found when they began looking closely at the smallest, faintest, most distant points of light scattered through it. Within days of the release, papers began appearing not months later, as is typical for careful astronomical analysis, but within days, because what researchers were seeing demanded an immediate second look. Scattered through the deep field, and through follow-up observations, were candidate galaxies at redshifts far beyond what anyone had expected to find so quickly. And they were not faint. Several of them were bright enough that, if their distances and ages were confirmed, they represented galaxies far more massive than the standard model of galaxy formation said should exist at that point in cosmic history. Much of the earliest and most consequential data came not from the widely circulated deep field images, but from dedicated survey programs, quieter in their public profile, but far more systematic in what they searched for. One of these, the Cosmic Evolution Early Release Science Survey, known within the field simply as SEERS, was designed specifically to hunt for galaxies at the highest redshifts Webb could reach. It scanned a modest patch of sky repeatedly, across multiple infrared filters, cataloging thousands of faint sources and sorting them by an observational technique astronomers call the dropout method, watching for galaxies whose light simply disappears from the bluer filters, a signature caused by intervening hydrogen gas absorbing everything at wavelengths shorter than a specific cutoff. A galaxy that drops out of enough filters, in the right pattern, is very likely sitting at extreme redshift. Its light stretch so far that shorter wavelengths never arrive at all. The astronomers running Sears and similar surveys were not looking for a crisis. They were looking for confirmation, a careful, methodical count of how many galaxies existed at each stage of cosmic history, the kind of foundational survey work that rarely makes headlines because it is not designed to. What they found instead was a discrepancy that grew harder to dismiss with every new data release. There were simply too many bright, massive candidate galaxies at redshifts above 10, not a handful of unusual outliers, which any survey expects to find by chance, but a population large enough that the standard model's predictions and the observed reality had visibly diverged. By early 2023, several independent teams had converged on the same unsettled conclusion, publishing analyses within weeks of one another, each reaching the finding from a different angle and arriving at the same place. The early universe was forming galaxies faster, bigger, and earlier than the equations said it should. Something in the models was incomplete. Nobody yet knew what. That uncertainty would not stay abstract for long. Within the flood of candidate detections, a small number of individual galaxies stood out clearly enough and were bright enough to warrant the kind of intensive follow-up observation that turns a statistical anomaly into a specific, named problem. A single point of light bright enough to demand an explanation of its own. It is worth pausing here, before moving into the specifics, to hold on to what kind of mystery this actually is. It is not a mystery about whether Webb's data can be trusted. The telescope's instruments have been calibrated and recalibrated, cross-checked against known reference stars, tested against every source of systematic error astronomers know how to test for. It is a mystery about interpretation, about what these bright, early, massive galaxies mean for a model of cosmic history that has otherwise matched observation after observation for decades. That distinction will matter a great deal as the specific cases come into view. The pattern that would eventually force this reckoning did not begin with a single dramatic announcement. It accumulated case by case across 3 years of observation, and to understand why any single galaxy could carry so much weight, it helps to meet the specific ones that did. Long before Webb, there was already a hint of what was coming. In 2016, using the Hubble Space Telescope, astronomers identified a galaxy called GN-Z11, sitting at a redshift of roughly 11, corresponding to a time about 400 million years after the Big Bang. At the time, it was the most distant galaxy ever confirmed, and it was already strange. It appeared unexpectedly bright for something so young, bright enough that some researchers wondered, quietly, whether the measurement had gone wrong somewhere. It had not. GN-Z11 was real. And it was an early signal, though almost no one recognized it as one yet of a pattern that Webb would later reveal in far greater detail. Some of the earliest and most striking of these detections benefited from a natural assist that has nothing to do with the telescope's own engineering. Massive galaxy clusters sitting between Earth and a distant target can act as gravitational lenses, their combined mass bending and magnifying the light of anything positioned behind them, in much the same way a glass lens bends light to magnify an object on the other side. Webb's first full-color deep field image, released in July 2022, was deliberately aimed at one such cluster, SMACS 0723, specifically because astronomers knew its gravity would magnify the light of background galaxies too faint to study directly otherwise. Several of the extreme redshift candidates found in that image, and others like it, owe part of their visibility to this effect. Genuinely distant, genuinely early galaxies, made observable only because a fortunate alignment of foreground mass happened to magnify their otherwise too faint light. This does not diminish the discoveries. It simply means some of the earliest candidates required this kind of cosmic assistance, while galaxies like JADESGS Z140 and MOME Z14, bright enough to be confirmed without relying on lensing magnification, represent an even more direct and less complicated case. Webb did not need to wait long to raise the stakes considerably beyond what GN-Z11 had hinted at. In February 2023, a team led by astronomer Ivo Labe published an analysis of 6 candidate galaxies spotted in Webb's earliest deep-field images that appeared to be almost impossibly massive for their apparent age, some seemingly holding as much mass and stars as the present-day Milky Way, at a point in cosmic history less than 700 million years after the Big Bang. The paper did not claim certainty. Candidate galaxies at this stage are identified through photometry, a technique that estimates redshift and mass from brightness across different filters, rather than through the more rigorous confirmation that spectroscopy provides. But the implications, if the estimates held, were severe enough that other astronomers in the field began referring to them, half seriously, as universe-breakers objects that, if confirmed, would leave the standard model of galaxy formation without an obvious way to explain them. Some of those 6 galaxies did not survive closer scrutiny. In 2024, follow-up spectroscopic observations found that at least one of the most extreme candidates was not nearly as massive as the initial photometric estimates suggested. A significant portion of its brightness, researchers determined, was coming not from starlight but from a rapidly feeding black hole at its center, an object called an active galactic nucleus, which can outshine the stars around it and, without more detailed spectroscopy, can be mistaken for evidence of a far larger stellar population than actually exists. This is worth sitting with for a moment, because it cuts against a simple narrative in either direction. It does not mean the impossible early galaxy problem disappeared. It means the field caught and corrected an overestimate, the way careful science is supposed to work, while genuine and more rigorously confirmed cases remained. GADES-GS-Z140 is one of those more rigorously confirmed cases. In 2024, a team analyzing spectroscopic data identified this galaxy, named for the JWST Advanced Deep Extragalactic Survey that found it. Its spectrum confirmed a redshift of 14.32, placing it at a moment roughly 300 million years after the Big Bang, when the universe was approximately 2% of its current age. For scale, if the entire history of the universe were compressed into a single calendar year, 300 million years after the Big Bang would fall somewhere in the first week of January. What set JADES-GS-Z140 apart from earlier candidates was not simply its distance. Distant, faint galaxies at extreme redshift were, by 2024, no longer shocking on their own. Webb had already found dozens of candidates in that territory. This galaxy stood out for its brightness and for spectroscopic confirmation solid enough that the black hole explanation, which had softened some of the 2023 candidates, did not apply here. It shone roughly 5 times brighter than the previous record holder, at similarly extreme redshift, and follow-up analysis estimated its mass at several 100 million times the mass of the Sun, a genuine galaxy, with organized structure, not a loose scattering of newborn stars still finding their shape. One astronomer working on the discovery, a researcher at the University of Arizona, said afterward that no one had expected galaxies this bright to exist at this redshift. That sentiment, in one form or another, would repeat across the field for the next 2 years. The record did not stand long. By 2025, a separate team had identified an even more distant candidate, cataloged as MOM Z14, with a confirmed redshift of 14.44, corresponding to roughly 280 million years after the Big Bang, about 2% of the universe's current age by an even tighter margin. As of this recording, MOM Z14 holds the distinction of being the most distant galaxy ever confirmed, detected first using Webb's near-infrared camera, and then verified spectroscopically using its near-infrared spectrograph, the instrument capable of confirming redshift with enough precision to rule out contamination or measurement error. Confirming a redshift this extreme is not a casual undertaking. Photometric estimates brightness measured across a handful of broad filters can suggest a candidate, but they carry real uncertainty, as the 2023 Universe Breaker episode demonstrated. Spectroscopy is the higher standard, splitting a galaxy's light into its full range of individual wavelengths and searching for the exact pattern created by the Lyman alpha break, a sharp cutoff caused by intervening hydrogen gas absorbing light below a specific wavelength. The location of that break, precisely measured, pins down the redshift with a level of confidence photometry alone cannot match. Both JADESGS-Z140 and MOM Z14 cleared that higher bar. Their distances are not estimates awaiting confirmation. They are, as far as the observational record allows, settled facts. Reaching that level of confirmation for MOM Z14 required a considerable amount of observing time, split across multiple instruments within Webb's suite. Its near-infrared camera first flagged the galaxy as a promising candidate, based on its dropout pattern across several filters. Confirming that candidacy meant pointing Webb's near-infrared spectrograph at the same faint point of light for an extended exposure, gathering enough individual photons, one at a time, from an object roughly 280 million years removed from the birth of the universe, to build a spectrum detailed enough to locate the Lyman alpha break precisely. This is not a quick observation. Extremely distant, extremely faint targets require correspondingly long exposure times, and survey teams have to be selective about which candidates are worth committing that much telescope time toward confirming. That MOM Z14 was chosen, and that the resulting spectrum held up under this level of scrutiny is itself a signal of how seriously the survey team treated the candidate from the beginning. These are not faint, ambiguous smudges of light either. Both galaxies were bright enough, and their spectra clean enough, that their extreme distances are not seriously disputed within the field. What remains genuinely unresolved is what their existence implies about how quickly galaxies can form, organize, and grow massive in the earliest chapter of cosmic history. A chapter the Standard Model predicted should look sparse, chaotic, and dim, not structured and bright. To understand why this matters as much as it does, it helps to walk through what building a galaxy actually requires, according to the Standard Model itself. In the earliest moments after the Big Bang, the universe was an almost perfectly smooth soup of hydrogen and helium, with only the faintest ripples of density variation. Gravity needed time to work on those ripples, pulling slightly denser regions together, slowly, patiently, across tens of millions of years, before the first stars could ignite. Those first stars needed more time still to form clusters, and those clusters needed yet more time to merge into the kind of organized, gravitationally bound structure that qualifies as a galaxy. Every step in that sequence takes time. The Standard Model does not simply guess at how much. It calculates it, using well-tested physics governing gravity, gas dynamics, and star formation efficiency, and those calculations set a floor on how quickly a bright, massive, structured galaxy, like JADESGS-Z140, should be able to assemble. There is a further wrinkle worth mentioning, because it complicates the picture even beyond raw mass and brightness. Several of the earliest Webb-discovered galaxies do not merely exist earlier than expected. Some also display internal structure, more organized than the Standard Model predicts for objects this young. A handful of candidates observed at redshifts above 6 show hints of disk-like rotation, an orderly, flattened structure similar in basic shape to spiral galaxies observed much closer to home, rather than the chaotic, clumpy, still assembling shape theorists expected the earliest galaxies to display. Disks form once a galaxy has settled into a stable gravitational configuration, which itself takes time ordinarily understood as a sign of relative maturity, not something expected in a galaxy only a few 100 million years removed from the universe's beginning. This detail rarely makes headlines the way distance records do. but among researchers modeling early galaxy formation, it has proven just as difficult to reconcile with the standard timeline as brightness and mass alone. 300 million years, by that floor, is uncomfortably tight. Not impossible in every version of the model, but tight enough that a galaxy this bright, this early, requires either an extraordinarily efficient process of star formation that the models had not fully accounted for, or something about the timeline itself needs revisiting. Both possibilities remain on the table. Neither has been ruled out. It helps, here, to sit for a moment with what a place like this would actually have looked like if there had been anything or anyone present to look. No planets yet, in any familiar sense. No heavy elements scattered through the space between stars, because those elements did not yet exist in any quantity. Only hydrogen and helium, gathered into vast dim clouds, collapsing here and there into the first true stars, stars unlike any that exist today, built from gas so pure and so metal-free that they could grow far larger and burn far hotter than anything the modern universe produces. Galaxies like JADESGSZ140 would have been assembling out of exactly this material, at a pace the standard model still struggles to account for, in a universe barely old enough to have finished its first few 100 million years of existence. And the tension only deepened when researchers began looking not just at how bright these early galaxies were, but at what they were made of. Distance and brightness, on their own, form a puzzle that theorists can still work around, given enough time and enough revision to their models of star formation efficiency. What happened next removed one of the easier escape routes, because in early 2025, spectroscopic analysis of JADESGSZ140 turned up something that made the timeline problem considerably harder to explain away, not a matter of how much light a galaxy produced, but of what that light revealed about the galaxy's internal chemistry, and what that chemistry should have taken far longer than 300 million years to build. When the only elements the universe knew how to make were hydrogen, helium, and a faint trace of lithium, nothing heavier existed. Not carbon, not nitrogen, not oxygen, not iron, not silicon, not any of the elements that make up rock, water, or a human body. The raw ingredients of nearly everything solid or breathing simply did not exist yet, anywhere in the whole of the universe. Those elements, astronomers, with characteristic bluntness, call everything heavier than helium a metal, regardless of whether it behaves like one had to be built, one atomic nucleus at a time, inside the cores of stars. This process is not fast. A star spends millions or billions of years fusing lighter elements into heavier ones within its core, and only releases those elements back into the surrounding gas when it dies, typically in a supernova explosion that scatters its enriched material outward. That scattered material then has to mix into the surrounding gas clouds, cool, and collapse again into a new generation of stars, a second generation, born from the wreckage of the first, carrying trace amounts of the heavier elements the first generation manufactured. Only after this cycle repeats, generation after generation, does a galaxy's gas accumulate enough oxygen, carbon, and nitrogen to register clearly in its spectrum. This is why astronomers use the presence and abundance of these elements as a kind of chemical clock. A galaxy rich in oxygen is a galaxy old enough, in terms of stellar generations, to have already lived through at least one full cycle of star formation, death, and rebirth. The nearby universe makes this clock easy to read, because nearby galaxies have had billions of years to run through countless such cycles. The Milky Way's own gas is thoroughly enriched, seeded by tens of billions of years of combined stellar deaths across its history, which is part of why planets, and eventually life, became possible here at all. The deep past should look nothing like this. A galaxy caught in its infancy, only a few 100 million years removed from a universe made of nothing but hydrogen and helium, should still be running its very first cycle. Young stars, freshly formed, not yet old enough to have died and enriched anything. Finding a fully measurable oxygen signature at that early stage does not fit the picture a young, first-generation galaxy is supposed to present. In early 2025, spectroscopic analysis of JADES GS Z140 detected exactly this signature, a clear, measurable abundance of oxygen present in a galaxy whose light left it roughly 300 million years after the Big Bang. It was, at the time, the most distant detection of a heavy element ever made, and the implications were not subtle. For that oxygen to exist, the universe needed to have already done something extraordinary in the small window available to it. It needed to have formed an initial generation of massive stars, allowed those stars to live out their comparatively short lives, let them explode and scatter their manufactured elements into the surrounding gas, allowed that gas to cool and gather again, and formed a second generation of stars from the enriched debris, all within roughly 300 million years of the universe's birth. To put that span in more familiar terms, it is a shorter stretch of time than it takes certain slow-growing trees on Earth to reach full maturity, and yet within it, the universe was expected to complete an entire cycle of stellar birth, death, and chemical rebirth. This is not, strictly speaking, impossible under the Standard Model. Massive, metal-free stars in the very early universe are predicted to be short-lived, burning through their fuel in a few million years, rather than the billions of years a star like the Sun requires, which does compress the timeline considerably. But compressing the timeline is not the same as comfortably explaining it, and researchers studying JADES GSZ140's chemistry have been candid about the difficulty. Building a second generation of stars, with measurable oxygen enrichment, inside 300 million years, asks the earliest phase of cosmic history to move with an efficiency the models had not been built to expect. The oxygen detection itself came with a further complication, one that took researchers by surprise almost as much as the enrichment timeline did. Alongside oxygen, spectroscopic analysis of several extreme redshift galaxies, including a reanalysis of GN Z1-1, the Hubble-era discovery mentioned earlier, turned up unusually high levels of nitrogen relative to what a galaxy this young should have produced. Nitrogen enrichment, in the standard picture of stellar nucleosynthesis, typically lags behind oxygen enrichment, building up gradually across additional generations of intermediate mass stars, rather than appearing this early or this abundantly. Finding nitrogen-rich gas in a 300 million-year-old galaxy compounds the chemical timeline problem rather than resolving it. One proposed explanation treats these unusual abundance patterns as evidence that the earliest star clusters may have resembled the dense, chemically unusual cores of present-day globular clusters, ancient, tightly packed groupings of stars found throughout the Milky Way's halo, long known for their own puzzling internal chemistry. If the earliest galaxies really did form through processes closer to globular cluster formation than the smoother, more gradual galaxy assembly the Standard Model typically assumes, that would help explain both the speed and the specific chemical signature Webb keeps finding. It would also mean the Standard Model's picture of early galaxy formation needs a more fundamental update than efficiency tweaks alone can provide. It helps, again, to slow down and picture the actual mechanics of what this cycle requires. A massive, metal-free star in the early universe burns hot and fast, its core fusing hydrogen into helium, then helium into carbon and oxygen, layer by layer, in a structure that resembles the layers of an onion, each shell fusing a heavier element than the one above it. When the star exhausts its fuel, the core collapses in on itself in a fraction of a second, and the outer layers rebound outward in a supernova explosion bright enough, briefly, to outshine every other star in its galaxy combined. That explosion is not simply destruction. It is delivery, the only mechanism the universe has for taking elements forged in a stellar core and scattering them out into the surrounding gas, where they can eventually become part of new stars, new planets, and Much later, new chemistry capable of supporting anything alive. Every oxygen atom in every breath taken by every living thing on Earth was manufactured this way, inside a star that died before the sun ever formed. The question posed by JADESGSZ140 is simply how many times this entire sequence, birth, fusion, death, delivery, rebirth, could plausibly repeat within 300 million years, and whether the answer the models currently give is generous enough to match what Webb is actually finding. JADESGSZ140 was not an isolated case. Around the same period, other survey teams began reporting similar findings, galaxies at high redshift carrying unexpectedly rich chemical signatures, more evolved in their internal composition than their extreme distance from us should have allowed. One line of investigation identified a cluster of early galaxies with metal abundances closer to what astronomers would expect from a galaxy several 100 million years older, prompting the same uncomfortable question each time. How did this much chemical processing happen this quickly, this early, over and over again, across multiple independently discovered galaxies, rather than one unusual outlier? Part of what makes this pattern so difficult to dismiss is how it was found. These are not cherry-picked examples, selected after the fact because they happen to support an interesting conclusion. They emerged from systematic surveys designed to catalog every sufficiently bright galaxy at these redshifts, without any prior expectation about what their chemistry would show. A survey built that way does not get to choose its results. It reports whatever it finds, and what several such surveys have found, independently of one another, is a recurring excess of chemically evolved galaxies sitting where the standard model predicted chemically primitive ones. The technique behind these measurements deserves a brief explanation, since it is easy to take the precision for granted. Astronomers determine a distant galaxy's chemical abundance not by directly sampling its gas, which is obviously impossible across billions of light years, but by measuring the relative brightness of specific emission lines within its spectrum, narrow spikes of light produced when electrons in specific atoms, excited by the intense radiation of nearby young stars, fall back to a lower energy state and release a photon of a very precisely defined wavelength. Oxygen produces several such lines at well-known wavelengths, and the ratio between them, combined with the ratio between oxygen lines and hydrogen lines produced by the same excited gas, allows astronomers to calculate the relative abundance of oxygen to hydrogen with real precision, even at extreme distance. This is not guesswork dressed up as measurement. It is a well-established technique, tested extensively on nearby galaxies where the results can be cross-checked against other methods, applied here to a target billions of light years further away than the technique was originally developed for. That repetition matters. A single strange galaxy can be explained away as a statistical fluke, a rare and unlikely alignment of circumstances that happen to produce one unusually fast-forming system. A pattern across multiple independently confirmed galaxies is harder to dismiss that way. Each new detection of early chemical enrichment adds another data point to a trend that, so far, keeps pointing in the same uncomfortable direction toward an early universe that built, burned through, and recycled its first generations of stars faster than the standard model's own physics predicted it should be able to. It is worth being precise about what has and has not been established here, because this is exactly the kind of finding that can be overstated in either direction. The oxygen detection itself is not seriously in dispute. Webb's spectrograph is sensitive enough, and the relevant emission lines distinct enough, that instrumental error is an unlikely explanation, and the finding has been checked against independent calibration standards. What remains open is the interpretation, whether the standard model simply underestimated how efficiently the early universe could form and recycle stars, in which case the timeline survives with revised assumptions about star formation efficiency, or whether the discrepancy is a symptom of something the model is missing entirely. Astronomers working on this problem are for the most part, betting on the former. Revising a model's assumptions about efficiency is a far smaller step than revising its account of cosmic time itself. But betting is not the same as knowing, and the honest position, for now, is that both possibilities remain open, with the second growing harder to dismiss every time a new early, chemically evolved galaxy is confirmed. There is a temptation, faced with a pattern like this, to reach immediately for the most dramatic possible explanation, to assume the entire model must be wrong, the age of the universe miscalculated, the whole framework due for demolition. The record does not yet support that leap. The more careful approach is not to rush toward the loudest possible answer, but to keep gathering the pieces in the order they were found and see where they actually lead. Oxygen in an impossibly young galaxy was one piece. Another piece, stranger still, was already accumulating in Webb's data, not in the chemistry of ordinary galaxies, but in a population of small, deeply red, and thoroughly confusing objects that had, by 2023, begun appearing by the hundreds across Webb's deepest fields, in numbers no one had predicted and no existing category of object seemed able to explain. The galaxies and their chemistry told one part of the story. A separate, quieter thread was unfolding at the same time, buried not in a handful of famous, individually named objects, but in a background population so numerous that it took time for anyone to notice a pattern at all. Not every mystery in Webb's data announced itself with a record-breaking distance or a striking chemical signature. Some of the strangest objects the telescope found were small, faint, and easy to overlook entirely until astronomers noticed how many of them there were and how consistently they shared a set of properties nothing in the existing catalog of cosmic objects quite matched. Astronomers came to call them little red dots, a name with no formal weight behind it, coined informally and then adopted so widely that it stuck. The objects earning the nickname were compact, often unresolved even at Webb's resolution, meaning they appeared as single points of light rather than extended structures. They were also, consistently, deeply red, not invisible light, since at these distances visible light is already redshifted out of range entirely, but in the pattern of their infrared brightness, which rose steeply toward longer wavelengths in a way that ordinary star-forming galaxies do not typically produce. Before Webb, these objects had simply never been seen. No previous telescope had the combination of sensitivity and infrared reach necessary to catch them. Once Webb turned its instruments toward the deep sky, they turned out to be common, not one or two unusual outliers, but hundreds of them, clustered in significant numbers, starting from roughly 650 million years after the Big Bang onward, and continuing to appear in survey after survey as Webb accumulated more observing time. Their abundance is itself part of the puzzle. Current estimates suggest little red dots may be dozens of times more numerous, per unit volume of early universe, than the population of ordinary quasars found at similar epochs by earlier surveys, a striking figure, if it holds up, because it implies either that overmassive black holes were far more common in the early universe than anyone had modeled, or that a meaningful fraction of the little red dot population is being misclassified as black hole dominated when some other, more mundane process is actually responsible. Sorting out which of these is correct requires exactly the kind of large, statistically robust sample that only continued observation can provide, and it is precisely this kind of demographic question, not the existence of the objects, which is well established, but their true nature and relative numbers that dominates the ongoing research into this population. Picture, for a moment, what one of these objects would look like up close, if such a thing were possible. Not a galaxy in any recognizable sense, no spiral arms, no scattered fields of individual stars, no visible structure at all. Just a single, searingly bright point, small enough that even a telescope capable of resolving detail across billions of light years cannot break it apart into anything more complex than a dot. Around it, presumably, a disk of infalling gas, heated by friction and gravity to temperatures bright enough to outshine everything nearby, feeding some central object whose exact nature remains, for now, a matter of careful argument rather than settled fact. Multiply that single point by several hundred, scattered across every deep field Webb has pointed its mirror toward, and the scale of the puzzle starts to come into focus, not one strange object, but an entire, previously invisible population of them, hiding in plain sight until an instrument finally arrived with the sensitivity to notice. Their sheer number was, on its own, a puzzle worth pausing over. But the deeper puzzle was what they actually were. A compact object this bright, at this redshift, radiating this much energy from a region small enough to remain unresolved even to Webb's sharp optics, fits uncomfortably with either of the two most obvious explanations. It is difficult to explain as an ordinary galaxy, because ordinary early galaxies at this epoch are expected to be extended, diffuse, actively forming stars across a recognizable structure, not compressed into an unresolved point. It also does not behave quite like an ordinary quasar, the bright, well-studied phenomenon produced when a supermassive black hole actively feeds on surrounding gas, because the color and spectral signature of the little red dots differs from typical quasar light in ways that took considerable analysis to characterize. The explanation that has gathered the most support treats these objects as a genuinely new category. Black holes, considerably more massive, relative to their host galaxies, than anything the local universe produces, caught in an early and unusually vigorous phase of feeding. Astronomers describe this relative imbalance using the ratio between a black hole's mass and the mass of the stars in its surrounding galaxy. In the nearby, well-studied universe, that ratio holds remarkably steady across galaxies of very different sizes, hovering around a consistent small fraction evidence. Most researchers believe that black holes and their host galaxies grow together, regulating each other's growth through the same feedback processes that keep star formation from running away unchecked. The little red dots break this pattern dramatically. Some appear to host black holes representing a far larger share of their total mass than the local ratio would predict, sometimes by a factor of 10 or more, as though the black hole had gotten a significant head start on a galaxy that has not yet caught up to it. In 2024, Webb observed direct evidence for just how vigorous that feeding could get. A black hole spotted at a point roughly 1.5 billion years after the Big Bang was found to be pulling in surrounding material at a rate around 40 times the theoretical limit normally used to describe how fast a black hole can feed without its own radiation pressure blowing the incoming gas away. That threshold, known as the Eddington limit, is not a hard physical wall, but exceeding it by such a wide margin is unusual enough that it demanded a specific explanation of its own, one candidate being that the geometry of gas flowing into an early, rapidly growing black hole may differ enough from the textbook model to allow this kind of extreme, sustained overfeeding. If black holes in the early universe really can grow this quickly, it helps explain at least part of the little red dot population, and it connects to a separate, equally unsettled question that has been circulating in the field for several years now. One that sounds almost like a riddle, stated plainly. Which came first? Galaxies or the supermassive black holes that sit at their centers? In the present-day universe, nearly every large galaxy, including the Milky Way, hosts a supermassive black hole at its core, and the two appear to have grown up together, their masses correlated closely enough that astronomers have long assumed the galaxy comes first, providing the gas and gravitational scaffolding a black hole eventually grows within. Webb has started turning up cases that complicate that assumption. One object, cataloged as QSO-1, appears to be a substantial black hole existing with little evidence of the massive host galaxy that current models say should have formed around it first. If black holes can form this early and grow this large without waiting for a fully assembled galaxy to provide the raw material, the traditional order of operations galaxy first Black hole second may not hold universally, at least not in the earliest chapter of cosmic history. The Eddington limit itself deserves a moment of explanation because it is not an arbitrary number. When a black hole pulls in surrounding gas, that gas heats up and radiates energy outward as it falls. At a certain feeding rate, the outward pressure of that radiation becomes strong enough to push back against the infalling material, creating a natural ceiling on how fast the black hole can grow. Under most conditions, a black hole feeding faster than this limit would simply blow its own fuel supply away, choking off the very process that was feeding it. A black hole sustaining 40 times that rate, as Webb observed in 2024, should not, by the standard picture, be physically stable. That it appears to have done so anyway suggests either a brief and unusually extreme episode, unlikely to last, or a geometry of infalling gas, perhaps a flattened, disc-like structure that allows radiation to escape more easily along certain directions, while gas continues falling in along others that the textbook version of the Eddington limit does not fully capture. Both explanations are being actively tested against further observations as they arrive. None of this resolves cleanly yet. Researchers studying the little red dot population remain divided over exactly what fraction are overmassive black holes. What fraction might be something else entirely? An unusual, compact, and very early stage of ordinary star formation, perhaps still not fully understood, and what fraction represents some hybrid of the two, a small galaxy with an outsized black hole embedded at its heart, each amplifying the other's already unusual light output. One promising line of evidence for the black hole explanation comes from a property that ordinary star-forming galaxies do not typically display: variability. Stars form and shine steadily over long stretches of time, and a galaxy's overall brightness, averaged across its full population of stars, changes only gradually across years or decades. Actively feeding black holes behave differently. The gas swirling into a black hole's accretion disk does not fall in smoothly. It clumps, flares, and occasionally dims as the flow of material fluctuates, producing changes in brightness that can register over weeks or months rather than centuries. When researchers went back and compared repeated observations of the same little red dots taken months apart, a meaningful fraction showed exactly this kind of short timescale flickering, a signature far more consistent with an actively feeding black hole than with any population of ordinary stars. This finding does not settle the question for every little red dot in the catalog, since not all of them show clear variability, but it has shifted the weight of evidence further toward the overmassive black hole explanation for at least a substantial portion of the population. An astrophysicist working on this problem at the Cosmic Dawn Center in Copenhagen described spending considerable time simply sketching the possibilities by hand, trying to visualize a class of object that does not yet fit cleanly into any established framework. That habit reaching for a pencil rather than a formula, when the formulas have stopped being enough on their own, says something about where this particular corner of astrophysics currently sits. It is not a field waiting quietly for one final measurement to settle things. It is a field actively improvising new ways to think about a population of objects the textbooks did not anticipate. That is, in its own way, an honest description of where the science currently stands. Not at a conclusion, but in the midst of genuinely open investigation, with new data arriving faster than the theoretical models can be revised to match it. What all three threads share: the bright early galaxies, the impossibly quick chemical enrichment, and now the little red dots, is a single underlying tension. Each one, independently, suggests that the first several 100 million years of cosmic history were more active, more productive, and more structured than the standard model predicted. Each one, independently, has survived serious scrutiny without a simple explanation emerging. And each one raises, a little more insistently than the last, a question the field can no longer avoid. What, exactly, would it take to explain all three at once? Faced with bright galaxies that formed too quickly, chemistry that enriched too fast, and black holes that grew too large too soon, the field of astrophysics did what it has always done when observation and prediction pull apart. It went back to the models, piece by piece, looking for an assumption that could reasonably be revised without discarding the entire framework. This is, in a sense, the ordinary machinery of science working exactly as intended, not panic, not a rush to declare the textbooks wrong, but a methodical search through every plausible adjustment before reaching for anything more drastic. 3 explanations have gathered the most serious attention. None of them requires abandoning the standard age of the universe. All 3 suggest that the early universe behaved differently, in specific and testable ways, than the models had assumed. The first candidate explanation involves something astronomers call bursty star formation. The standard model, in its simplest form, tends to treat star formation as a relatively steady process. Gas collapses, stars form at a rate that changes gradually over cosmic time, rather than in sudden surges. But there is growing reason to think that early galaxies, still small and still gravitationally chaotic, may have formed stars in short, intense bursts, rather than a smooth ongoing trickle. A galaxy caught by Webb during one of these bursts would appear far brighter than its average, underlying stellar population would suggest, simply because of when the snapshot was taken. This matters statistically as much as it matters for any single galaxy, because a population of galaxies undergoing frequent, intense bursts will contain a small number caught at unusually bright moments, and a survey that happens to find those bright moments can overestimate how common and how massive early galaxies typically are, an effect closely related to something called Eddington bias, where the brightest, most easily detected members of a population get counted more often than the true underlying distribution would suggest, simply because they are the easiest ones to see. It helps to picture this with an ordinary comparison. Imagine trying to judge the average height of a crowd by only noticing the people tall enough to see over a fence. The measurement is not wrong. Exactly those people really are that tall, but the sample is skewed toward the exceptional cases, because the exceptional cases are the only ones visible from where the observer is standing. A survey searching for extremely distant, extremely faint galaxies faces something similar. The galaxies caught mid-burst, glowing brighter than their average state, are simply easier to detect against the deep, dark background of space than galaxies caught during a quieter phase of star formation. If bursty star formation really is common in the early universe, some fraction of the apparent overabundance of bright early galaxies may reflect this detection bias rather than a true excess of massive galaxies at these redshifts. The second candidate explanation concerns the internal makeup of the very first stars, a generation astronomers refer to as population 3 stars, theorized but never yet directly observed. Stars forming today, including the Sun, form from gas already enriched with heavier elements from billions of years of prior stellar generations, and that enrichment shapes how stars form smaller. Cooler stars tend to be more common than very large, hot ones, a pattern astronomers describe using something called the initial mass function. The very first stars in the universe formed from gas with none of that enrichment, pure hydrogen and helium, nothing heavier. Some researchers argue that this pristine gas may have produced a fundamentally different mix of stars, weighted more heavily toward extremely massive, extremely luminous stars than the mix seen in the modern universe, what the field calls a top-heavy initial mass function. A population weighted this way would produce far more light per unit of stellar mass than models built on modern assumptions predict, which would make an early galaxy appear more massive, from its brightness alone, than it actually is in terms of total stars formed. The physical reasoning behind this idea is fairly intuitive once laid out. Gas enriched with heavier elements cools more efficiently than pure hydrogen and helium, because those heavier elements provide additional ways for the gas to radiate away energy as it collapses. Cooling efficiently allows a collapsing cloud to fragment into many smaller pieces, each one forming a comparatively modest star, which is roughly what happens in the modern, metal-rich universe, where small and medium stars vastly outnumber giants. Pure, metal-free gas cools far less efficiently. It tends to collapse in fewer, larger clumps, each one forming a single, unusually massive star, rather than fragmenting into many smaller ones. If this reasoning holds at the scale of an entire early galaxy, the first generation of stars anywhere in the universe would have skewed dramatically toward the massive end of the scale, exactly the population needed to make a young galaxy shine far brighter than its total stellar mass would otherwise suggest. The third candidate explanation is closely related to the first two, but focuses on efficiency rather than burstiness or stellar mix, and it may ultimately prove to be the most important of the three, since it interacts with and amplifies the effects of the other two rather than standing entirely apart from them. In the modern universe, the process of turning available gas into stars is fairly inefficient. Most of the gas in a galaxy never actually collapses into a star at all, dispersed instead by stellar winds, radiation pressure, and supernova explosions before it gets the chance. Some models now propose that early galaxies, smaller and with weaker stellar feedback to push gas away, may have converted their available gas into stars with far greater efficiency than the modern universe typically manages, essentially building bigger, brighter galaxies out of a comparatively modest supply of raw material, because so little of that material went to waste along the way, unlike the wasteful, inefficient process that dominates star formation in galaxies like our own today. Several major simulation projects have taken up this challenge directly, each modeling slightly different combinations of these effects across a simulated volume of early universe designed to be statistically representative of the real thing. One such project, known as flares, focuses specifically on the rare, extreme overdensities most likely to produce the brightest early galaxies, running detailed physics on these unusual regions rather than a more average patch of simulated sky. Another, called Thiessen, places particular emphasis on how radiation from early stars and black holes reionize the surrounding hydrogen gas, a process closely tied to how efficiently early galaxies could keep forming stars in the first place. Comparing the outputs of these different projects against Webb's actual observations has become one of the primary ways researchers test whether standard physics, generously but plausibly tuned, can really account for what the telescope keeps finding. The results so far are mixed in an informative way. Some simulations comfortably reproduce the brightest observed galaxies, others fall noticeably short, and the gap between the two often comes down to exactly how aggressively a given simulation allows for burstiness, top-heavy stellar populations, or formation efficiency, which is itself a reminder that these three explanations are not fully independent of each other. They interact, sometimes reinforcing one another, and sometimes trading off, in ways that make isolating a single dominant cause difficult, even within a controlled simulation. Dust plays a role in this picture too, one easy to overlook. Interstellar dust, fine grains of heavier elements condensed out of the same enriched gas discussed in the previous chapter, absorbs starlight and re-emits it at longer wavelengths, which means a dusty galaxy can appear fainter than its true stellar population would suggest. Early galaxies, having had less time to build up dust from successive generations of dying stars, are generally expected to be less dust-obscured than galaxies observed later in cosmic history, which is part of why their brightness stands out so clearly. But this cuts in an uncomfortable direction for some of the standard explanations. If early galaxies are as dust-poor as expected, that removes one plausible way their brightness could be partially explained away and strengthens the case that the light being observed really is coming from a genuinely large, genuinely luminous population of young, hot stars, rather than a smaller population whose faintness happens to be masked by unusually low dust content. It requires modeling the gravitational collapse of gas clouds, the birth and death of individual generations of stars, the feedback effects of radiation and supernovae pushing gas around, and the cumulative brightness that results all across a volume of simulated space meant to stand in for a representative slice of the early universe. Getting all of these processes to interact correctly at the right relative strengths is delicate work, and small changes in the assumptions fed into the simulation can shift the results considerably. That sensitivity cuts both ways. It means the models are flexible enough to potentially accommodate what Webb is finding. It also means researchers need to be careful not to simply tune the assumptions until the answer comes out right, a trap that good simulation work is specifically designed to guard against through independent testing and comparison across research groups. This is, for many in the field, the most likely resolution. Not a single silver bullet explanation, but early universe physics that behaved somewhat differently than assumed, in ways the models are gradually being updated to reflect. But gradually is the important word here, and it is worth taking seriously rather than treating as a hedge. These explanations remain under active testing, refined and challenged with each new observation, and none has yet achieved the kind of broad, settled consensus that would close the question entirely. The oxygen problem, in particular, sits somewhat uncomfortably alongside these solutions. Bursty star formation and a top-heavy initial mass function can explain why a galaxy looks brighter than expected, but they do less on their own. To explain how that galaxy's gas became chemically enriched on a timescale the standard cycle of stellar death and rebirth finds difficult to accommodate. Combining efficient star formation with a very rapid succession of short-lived, massive first-generation stars gets closer, but the fit remains tighter than most researchers would prefer. There is a fourth possibility, quieter than the other three, and less frequently discussed outside specialist circles, worth mentioning briefly here. Some researchers have proposed that the earliest black holes, rather than forming exclusively from the collapse of massive first-generation stars, may have formed through a more direct process, the collapse of an unusually dense pocket of primordial gas straight into a black hole, skipping the intermediate stage of stellar life and death entirely. A black hole seeded this way would start out far more massive than one built gradually from a stellar remnant, giving it a substantial head start on the kind of rapid growth needed to explain objects like the little red dots. This idea remains speculative, difficult to test directly, and is not yet treated as a leading explanation by most of the field. But it illustrates something true about the state of this research generally. Even the more conventional, non-radical side of this debate includes ideas that would have sounded unusual only a few years ago, before Webb's observations made some kind of revision to early universe physics necessary in the first place. And for a smaller group of researchers, close is not close enough. If the standard explanations require stretching several independent assumptions to their limits, simultaneously burstiness, stellar mix, and formation efficiency all push toward their most extreme plausible values. At the same time, across multiple independently discovered galaxies, then perhaps the more honest response is to ask whether something more fundamental about the timeline itself deserves a second look. That question does not belong to a fringe corner of the field, dismissed and ignored by serious researchers. It belongs to a small but persistent minority working within peer-reviewed cosmology, publishing analyses in the same journals as everyone else, arguing that the accumulated weight of evidence, the bright galaxies, the rapid enrichment, the overmassive black holes, all converging on the same uncomfortably narrow window of cosmic time, might be pointing toward a genuine gap in the standard model, rather than a set of coincidentally aggressive, but ultimately explainable early universe conditions. Their proposals are more radical than adjusting star formation efficiency. Some of them touch the age of the universe itself, and it is to those proposals, carefully and without exaggeration, that this account turns next. Before going further, it is worth being precise about what kind of claim comes next. because this is the point in the story where careful science and speculation are easiest to blur together. And the honest approach here has always been to slow down rather than speed up. The overwhelming majority of working cosmologists remain confident that the universe is approximately 13.8 billion years old, a figure derived not from any single measurement, but from multiple independent lines of evidence that agree with each other to a high degree of precision. The cooling pattern of the cosmic microwave background, the observed rate of cosmic expansion, the ages of the oldest known stars, and the abundance of light elements produced in the universe's first few minutes. Each of these methods works entirely independently of the others. The cosmic microwave background is a snapshot of radiation released roughly 380,000 years after the Big Bang. Its faint temperature variations still readable today, with instruments sensitive enough to measure differences of millionths of a degree. The ages of the oldest stars are calculated from stellar physics that has nothing directly to do with cosmology at all, based on how long a star of a given mass takes to burn through its nuclear fuel. That method's this different, measuring entirely different physical phenomena, converge on the same age within a narrow margin of uncertainty is one of the strongest results in modern physics. And it is not casually overturned by a population of unusually bright, early galaxies. However genuinely puzzling those galaxies remain. Most researchers studying the impossible early galaxy problem are looking for a solution within this framework, not a replacement for it. But a small number of published, peer-reviewed proposals do exactly that. They ask what would happen if the standard age were wrong, and they do so using the same observational data everyone else is working from. One line of argument, associated with astrophysicist Rajendra Gupta and collaborators, proposes a modification to the standard cosmological model that would push the universe's true age significantly higher than 13.8 billion years, in some versions closer to 26 or 27 billion years. The core idea involves reconsidering how certain physical constants, such as the strength of the forces governing particle interactions, might have varied gradually over cosmic history rather than remaining perfectly fixed, combined with revisions to how the expansion of space itself is modeled at very early times. If true, a universe with significantly more elapsed time before the era Webb is observing would remove much of the pressure created by the impossible early galaxy problem. 300 million years stops being a tight constraint if the actual age of the universe at that observed redshift is substantially longer than the standard model calculates. This kind of proposal is not dismissed outright by the field, because a genuine anomaly deserves genuine alternative explanations, and cosmology has revised its assumptions before in response to unexpected data. The discovery that the universe's expansion is accelerating, made in the late 1990s, forced exactly this kind of revision, introducing the concept now called dark energy into a model that had not previously required it. Before that discovery, most cosmologists expected the expansion of the universe to be slowing down, pulled inward by the combined gravity of everything within it. The observation that distant supernovae were fainter, and therefore farther away, than a slowing expansion would predict, forced the field to accept something it had not been looking for, and had no immediate explanation for. That episode is often cited by researchers proposing more radical solutions to the early galaxy problem, as evidence that cosmology should remain open to comparably large revisions when the data insists on it. But it is also cited by researchers skeptical of those same radical solutions, as a reminder that such revisions are rare, hard-won, and only accepted once they survive a level of scrutiny the current alternative age proposals have not yet passed. But it is also not close to broadly accepted, and it is worth understanding exactly why. Modifying fundamental constants, or the expansion history of the universe, has consequences that extend far beyond solving the early galaxy problem. The same framework used to calculate the universe's age also successfully predicts the detailed pattern of temperature fluctuations in the cosmic microwave background, the observed abundances of hydrogen, helium, and lithium produced moments after the Big Bang, and the large-scale structure of galaxies observed across the modern universe. Any modification serious enough to double the universe's age needs to also preserve all of these other successful predictions simultaneously, without introducing new contradictions elsewhere. That is an extremely demanding requirement, and so far, alternative models proposing a much older universe have not managed to match the standard model's success across this full range of independent evidence. They solve one problem while, to date, leaving several others unresolved or untested. There is also a simpler and more immediate objection worth stating plainly. If the universe's true age were closer to 26 billion years, the redshift to time conversion astronomers use to date every observation would itself need substantial revision, which would change the calculated ages, not just of the puzzling early galaxies, but of essentially everything else Webb and other telescopes have measured. Some of that recalculated chronology would need to still make physical sense. Stars within galaxies would need to be younger than their host galaxies. Elements would still need time to form in the sequence physics requires, and the broader structure of cosmic history would need to remain internally consistent. Researchers who have examined these more radical proposals in detail have generally found tensions of exactly this kind. Cases where solving the early galaxy problem creates a comparably awkward problem somewhere else in the model. There is a broader pattern worth noticing here, one that shows up whenever a field confronts a genuine anomaly. The first instinct, almost always, is to look for a solution that disturbs the least amount of existing, well-tested knowledge, adjust an assumption about star formation, revise an efficiency parameter, account for a detection bias. Only when those smaller adjustments consistently fail to close the gap does serious attention shift toward larger revisions, the kind that touch fundamental constants or the expansion history of the universe itself. Cosmology has not reached that second stage yet, not because researchers are reluctant to consider it, but because the smaller adjustments described earlier in this account have not yet been definitively ruled out. Bursty star formation, a top-heavy initial mass function, and enhanced formation efficiency remain live, testable possibilities, and most of the field's energy is currently directed at testing them more precisely rather than reaching past them toward a modified cosmology. This does not mean the more radical proposals are worthless. It means they remain, for now, a minority position within active, ongoing scientific debate, tested seriously and found, so far, incomplete rather than definitively wrong. Science treats incomplete and wrong very differently. An incomplete proposal stays on the table, refined and retested as new data arrives. A wrong proposal gets set aside, where a given idea falls between those two categories. At any given moment, is itself part of what makes this kind of live scientific question worth following closely, rather than waiting for a textbook to eventually summarize the outcome. What can honestly be said is this: the standard age of the universe remains the best supported figure available, resting on multiple independent lines of converging evidence that a handful of puzzling early galaxies has not yet overturned. At the same time, those galaxies represent a real and unresolved tension within that same Standard Model 1. The field is not fully explained through star formation efficiency, stellar mix, or observational bias alone, and one that a small minority of researchers believe points towards something more fundamental. Both of these statements can be true simultaneously, and holding them together without collapsing toward false certainty in either direction is the most accurate way to describe where this particular scientific question currently stands. There is a second reason, beyond the internal consistency problem, that the more radical proposals face such a steep climb toward acceptance, and it has to do with how scientific consensus actually forms rather than with the proposal's technical merit alone. A new idea in physics rarely displaces an established framework simply by explaining one stubborn anomaly better than the alternatives. It generally has to do more than that, predict something new, not yet observed, that the standard model does not predict, and then have that prediction confirmed by independent observation. General relativity did not simply patch Mercury's orbit. It also predicted that starlight passing near the Sun would bend by a specific, calculable amount, a prediction confirmed during a solar eclipse in 1919 in an observation that had nothing to do with Mercury at all, and that convinced much of the physics community far more decisively than the original orbital calculation had. The age revision proposals currently on the table have not yet produced a comparably distinct, independently testable prediction of this kind. Until one does, and until that prediction is checked against real data, the proposal remains a candidate explanation for one specific anomaly rather than a genuine rival to the framework it hopes to replace. This is not a uniquely high bar invented to protect the standard model from criticism. It is the same bar every major revision in the history of physics has eventually had to clear, including the revisions that succeeded. Quantum mechanics did not gain acceptance because it explained the puzzling behavior of light on its own. It gained acceptance because it went on to correctly predict entirely separate phenomena nobody had yet observed across chemistry, materials, science, and eventually electronics, in ways that classical physics could not. Plate tectonics, similarly, did not persuade geologists simply by explaining the shapes of continental coastlines. It persuaded them once it also correctly predicted patterns of magnetic striping on the ocean floor, discovered independently, that classical geology had no way to account for. A proposal that revises the age of the universe will likely need to clear a similar bar, not simply fitting the impossible early galaxy data after the fact, but predicting some other, independently checkable feature of the cosmos that the standard model gets wrong and the revised model gets right. That is a demanding standard, and it is demanding for good reason. None of this means the question is closed, or that the researchers pursuing these more radical ideas are working outside the bounds of legitimate science. Peer review exists precisely to test claims like these, rigorously and repeatedly, against exactly the kind of scrutiny described here. Some fraction of unconventional proposals in the history of physics have eventually proven correct, after years of being treated as a minority position. Most have not. The impossible early galaxy problem does not yet reveal which category its more radical proposed solutions will ultimately fall into, and pretending otherwise, in either direction, would misrepresent how unsettled this particular corner of the field actually is. It helps, in fact, to look directly at how earlier anomalies like this one actually played out, because the history of cosmology offers more than one useful precedent for exactly this kind of extended, unresolved tension. This kind of extended uncertainty is not unusual in cosmology, even if it can feel unsettling from the outside, and the field has weathered comparable periods of open tension before. Looking closely at a few of those earlier episodes offers a useful sense of what a genuine, unresolved anomaly actually looks like, while it is still being worked out, in real time, without the benefit of hindsight, and what it eventually took, in each case, for the field to find its footing. The first began quietly, in the 1970s, with an astronomer named Vera Rubin measuring how fast stars orbit around the centers of spiral galaxies. By the physics available at the time, stars farther from a galaxy's center should orbit more slowly than stars closer in, the same way planets farther from the Sun move more slowly than planets close to it, because the gravitational pull holding them in orbit weakens with distance. Rubin's measurements did not show that pattern. Stars far out at the edges of the galaxies she studied were orbiting just as fast as stars much closer to the center, which made no sense if the only mass present was the visible mass astronomers could actually see and measure through starlight. Rubin herself, working alongside astronomer Kent Ford, using an unusually sensitive spectrograph Ford had built, was careful and thorough about ruling out simpler explanations before suggesting anything unusual. She checked her instruments. She checked her calibrations. She measured galaxy after galaxy, dozens of them eventually, and the flat rotation pattern kept appearing, consistently, regardless of which galaxy she pointed her instrument toward. This kind of patient, repeated verification, galaxy after galaxy, is precisely the same pattern now playing out with Webb's early galaxy candidates, a single unusual result treated with suspicion, a repeated result treated as a genuine phenomenon, requiring explanation. It is worth noting, too, that Rubin's own results were not immediately embraced, even after this careful verification. Some colleagues suggested the effect might be an artifact of how gas, rather than stars, move through a galaxy's outer regions, or proposed other conventional astrophysical explanations, before conceding that none of them adequately fit the data. Acceptance, when it came, arrived gradually, built through repetition and cross-checking, rather than through any single decisive moment. The parallel to the present mystery is not exact. No two scientific episodes ever map onto each other perfectly, but the shape of the process, patient accumulation before confident conclusion, tends to repeat across very different corners of the field. For years, this discrepancy sat exactly where the impossible early galaxy problem sits now. Confirmed, repeated across galaxy after galaxy, resistant to easy dismissal, and without an agreed explanation. Some researchers wondered whether the laws of gravity themselves needed revision at galactic scales, a proposal not unlike the more radical age revision ideas discussed earlier in this account, in that it questioned something fundamental, rather than adjusting a smaller assumption. Others suspected some invisible source of additional mass, undetectable by light, but present in large enough quantity to explain the extra gravitational pull. Neither camp could immediately prove its case. The observations kept accumulating, and the argument continued, unresolved, for well over a decade. What eventually tipped the argument was not one single measurement, but a converging weight of independent evidence. Studies of how galaxy clusters bend light through a phenomenon called gravitational lensing showed mass distributed in patterns that matched an invisible component far better than they matched a simple revision to gravity's law. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang itself, showed patterns of density variation that only made sense if a form of matter interacting weakly with light, but strongly with gravity, was present throughout the early universe in large quantities. Computer simulations of how galaxies form and cluster over cosmic time only matched the observed large-scale structure of the universe when this invisible mass was included as a fundamental ingredient. Piece by piece, across different techniques, different research groups, and different kinds of observation entirely, the case for what astronomers now call dark matter built to the point of broad acceptance. It is still, to this day, not directly detected in any laboratory. Its presence is inferred entirely from its gravitational effects, and it remains one of the largest unresolved questions in physics, in the sense that nobody yet knows precisely what it is made of. But its existence, as a component of the universe, is no longer seriously disputed. It took roughly 2 decades from Rubin's first puzzling measurements to that broad acceptance, and the process, while long, unfolded in exactly the plodding, evidence-by-evidence manner that characterizes careful science working through something it does not yet fully understand. The second episode is more recent, and still, as of this recording, entirely unresolved. Astronomers have 2 independent ways of measuring how fast the universe is currently expanding, a value known as the Hubble constant. One method starts from the nearby universe, measuring the distances and velocities of relatively close galaxies using well-established techniques involving certain kinds of pulsating stars and exploding stars, whose intrinsic brightness is well understood. A method built up carefully, step by step, using nearby objects with known distances to calibrate each successive rung of a ladder that eventually reaches out to distant galaxies. The other method starts from the cosmic microwave background, using the detailed pattern of that ancient afterglow to calculate, indirectly, what the expansion rate should be today, based on the standard cosmological model run forward from the very beginning of the universe. These 2 methods, measuring conceptually the same quantity from two entirely different directions, should agree. For over a decade now, they have not. The discrepancy is not large, a matter of a few percent, but it is consistent. It has grown more statistically significant as measurement precision has improved rather than less, and it has resisted every attempt so far to explain it away as a simple calibration error in either method. Researchers refer to this open problem as the Hubble tension, and it occupies a strange, uncomfortable position within the field, not unlike the impossible early galaxy problem now does. It is taken seriously by essentially the entire field, unlike some more speculative anomalies that fade after further scrutiny. Once a simple measurement error is finally tracked down, it has resisted every conventional explanation offered so far, including recalibrations of both measurement techniques, revised assumptions about the specific stars used as distance markers, and careful re-examinations of the microwave background data itself. And it remains genuinely unresolved, without the field having settled on whether the answer will turn out to be some overlooked systematic error in one of the two measurement techniques, or something more fundamental about the standard cosmological model that will need to be revised once the true explanation is finally identified. What both of these episodes share, and what makes them useful to hold alongside the current mystery, is the shape of their unresolved middle period long stretches of time in which the anomaly was real, confirmed, and stubbornly resistant to easy explanation, without the field being able to say yet exactly how the story would end. Dark matter eventually resolved, after 2 decades, into something close to consensus, even though its deepest nature remains unknown. The Hubble tension has not resolved at all, more than 10 years after it was first taken seriously, and continues generating new proposed explanations and new measurements with no end clearly in sight. Both outcomes remain possible for the impossible early galaxy problem. Nothing about the current uncertainty guarantees which path it will follow, and nothing about the field's history offers a reliable way to predict how long that path will be. There is a third, older pattern worth mentioning briefly, if only because it cuts in the opposite direction, as a reminder that not every anomaly survives its early scrutiny. In the late 19th century, astronomers studying the orbit of Mercury noticed a small, persistent discrepancy between where Newtonian gravity predicted the planet should be and where it actually was, a tiny drift in its orbit that no amount of careful remeasurement made disappear. For decades, some astronomers proposed an entirely new, undiscovered planet, tentatively named Vulcan, orbiting even closer to the Sun than Mercury, whose gravitational tug would account for the discrepancy. Some observers even claimed to have glimpsed it, briefly. Crossing in front of the Sun reported sightings that generated real excitement within the field before failing, one after another, to be confirmed by follow-up observation. Careful searches never found it. The actual resolution, when it arrived in 1915, required something far more sweeping than a new planet. Einstein's general theory of relativity, which described gravity itself differently than Newton had, and which predicted Mercury's exact orbital drift as a natural consequence of its proximity to the Sun's mass, without requiring any additional unseen object at all. Newtonian gravity was not simply patched. It was superseded by a deeper theory that happened to reduce back to Newton's equations under most everyday conditions, which is part of why the transition, disruptive as it was, did not throw out everything that came before it. 3 episodes, 3 different outcomes. An invisible new form of matter, inferred correctly, and eventually confirmed through multiple independent lines of evidence, even though its fundamental identity is still unknown. A tension in measurement that, decades later, still has no agreed resolution at all, generating new candidate explanations faster than any of them can be conclusively tested. A hunted planet that turned out not to exist, because the actual answer required rethinking gravity itself, rather than searching for one more hidden object out past Mercury's orbit. Cosmology, and physics, more broadly, has produced examples of all three outcomes before, which is exactly why researchers studying the impossible early galaxy problem are reluctant to guess too confidently. This early, at which pattern their own mystery will eventually follow. It is tempting, at the end of an account like this one, to reach for a clean resolution, a single sentence that ties the bright galaxies, the early oxygen, the little red dots, and the debate over the universe's age into one tidy conclusion. The kind of ending that would make for a satisfying final chapter. The honest record does not currently offer one, and manufacturing a false sense of closure would do a disservice to exactly the kind of careful, evidence-based thinking this whole account has tried to model. What it offers instead is a clearer picture of exactly where the uncertainty lives, which is its own kind of progress. Even if it does not resolve into the kind of answer a shorter, simpler account might have preferred to give. It may help, before drawing this together, to hold the three earlier episodes just described alongside the specific findings this account has traced from the beginning, and ask plainly which of those earlier patterns the current evidence most resembles. Here is what can be said with real confidence. The James Webb Space Telescope has found galaxies at redshifts, and therefore ages, beyond what almost anyone expected to observe this early in the mission. JADES, GS, Z140, and MOM, Z14 are real. Their distances confirmed through spectroscopy rather than the more uncertain photometric estimates that produced some of the earlier, later revised candidates. The oxygen detected in JADES GSZ 140's spectrum is real, measured with enough confidence that instrumental error is not a serious competing explanation. The little red dots are real, present in Webb's data by the hundreds, sharing a set of properties that no single previously known category of object fully explains. Each of these findings has been checked, cross-checked, and largely confirmed by independent teams working from the same underlying data. This is not a case of one research group's unusual interpretation being mistaken for a broad scientific consensus. It is closer to the opposite. A wide, methodologically diverse set of research groups, using different instruments within Webb's suite, different analysis techniques, and in some cases, different survey fields entirely, independently arriving at findings that reinforce rather than contradict one another. That kind of convergence across independent groups with no particular incentive to agree is exactly the pattern that gives a scientific finding real weight, regardless of how uncomfortable that finding might be for the existing theoretical framework. It is worth being clear about the distinction this draws. The raw observations are not in question. What remains genuinely open is only what those observations, taken together, ultimately mean. Here's what remains genuinely unresolved, stated as plainly as the evidence currently allows. Whether the standard model of galaxy formation can be adjusted through bursty star formation, a top-heavy initial mass function, enhanced formation efficiency, or some combination of the three to fully accommodate these findings without further revision. Simulations suggest this is plausible for the brightness problem alone, less certain once the oxygen enrichment timeline is factored in, and more strained still once the overmassive black holes are added to the same picture. Whether some genuinely new physics, short of revising the universe's fundamental age, might be needed to close the remaining gap, a possibility researchers are actively exploring, using explanations more modest than the more radical age revision proposals, but still beyond the current standard toolkit. And whether, as a small minority argue, the anomaly is severe enough to eventually justify reconsidering assumptions about cosmic time that have otherwise held for decades. No published analysis, as of this recording, has managed to close all three of these open questions at once, and any account that claims otherwise is getting ahead of what the evidence currently supports. The impossible early galaxy problem may follow a path similar to the dark matter story. Years of incremental testing, competing explanations narrowed one at a time, before the field arrives at whatever answer the evidence eventually supports. It may also resolve faster if a single decisive observation, a spectrum precise enough, a sample large enough settles the question more cleanly than the dark matter or Hubble tension stories did. It could equally drag on for another decade, gathering additional strange objects and additional partial explanations without ever quite reaching the kind of clean resolution either side of the debate would prefer. Closer to the ongoing, still open shape of the Hubble tension than to dark matter's eventual convergence. Nobody currently knows which path this particular mystery will take, and that uncertainty is not a gap in the reporting. It is an accurate description of where the science currently stands. What makes this moment particularly interesting, rather than simply unresolved, is how quickly new data continues to arrive. Webb is not finished. Its planned operational lifetime extends for many more years, limited primarily by the finite supply of propellant needed to maintain its orbit around L2, carefully budgeted to stretch the mission as long as possible, with recent fuel efficiency estimates suggesting the telescope may operate for 2 decades or more, rather than the roughly 10 years originally projected at launch. And each new observing cycle brings additional candidate galaxies at extreme redshift, additional spectroscopic confirmations, additional detail on the population of little red dots. Ground-based observatories currently under construction, including extremely large telescopes with mirrors far bigger than Webb's, will eventually add complementary data from angles Webb cannot cover alone, using different techniques capable of testing some of the same questions from an entirely independent direction. The picture available at the time of this recording is not the final picture. It is a snapshot of an active investigation, midway through, with real stakes and no guaranteed outcome, still being written by researchers who do not yet know how their own current papers will read once the next round of data arrives to either support or complicate them. It is worth remembering, too, that the people doing this work are not detached observers watching from a comfortable distance. They are scientists who trained for years to understand a model they largely trusted, who now find themselves needing to hold 2 things at once: genuine excitement at having discovered something the textbooks did not predict, and genuine discomfort at not yet knowing what that discovery ultimately requires them to revise. That combination, excitement paired with discomfort, rather than either one alone, tends to produce careful work rather than rushed conclusions in either direction. Nobody studying this problem wants to be the researcher who prematurely declared the standard model broken, only to have a more mundane explanation quietly resolve the tension a few years later. Nobody wants to be the researcher who dismissed a genuine anomaly too quickly, either clinging to a comfortable framework past the point the evidence could still support it. Both mistakes have happened before, in other corners of this field's history, and the caution running through this account reflects an entire scientific community trying, visibly, to avoid repeating either one. That caution is worth distinguishing from indecision, because the two can look similar from the outside but mean very different things. Indecision would mean the field has no idea what is going on and no way to make progress. That is not the situation here. Researchers have ruled out entire categories of explanation already. Instrumental error, for instance, is no longer a serious contender, given how many independent teams, using different equipment configurations and different analysis pipelines, have confirmed the same basic findings. What remains is a narrower, more specific disagreement about which of several plausible physical explanations, or which combination of them, accounts for what is actually being observed. That is real progress, even though it does not yet look like a finished answer. Ruling things out is how every open scientific question eventually narrows toward a resolution, and the impossible early galaxy problem has already been narrowed considerably since the first strange candidates appeared in 2022. What began as a single confusing deep field image, with a handful of oddly bright smudges scattered through it, is now a structured, well-defined set of testable hypotheses, each with specific predictions that future observations can confirm or rule out in turn. That transformation, From vague puzzlement to organized investigation, is itself a form of progress worth recognizing, even in the absence of a final answer. There is something worth sitting with in that fact itself, apart from any specific resolution to the puzzle. Most of what a documentary like this one covers concerns events long finished extinctions that concluded tens of millions of years ago. Civilizations that rose and fell before anyone alive today was born. Cosmic processes that completed their work before the Earth existed to witness them. Even when those subjects remain surrounded by open scientific questions, the underlying event itself is over, fixed in the past, available for study but no longer in motion. This account is different. The mystery it describes is still unfolding, its resolution still unwritten, its next chapter dependent on observations that have not yet been made. The galaxies themselves finished forming billions of years ago. Of course, their light left them long before Earth existed. But the human understanding of what that light means, the part of this story that actually constitutes the mystery, is happening now, in papers being drafted, submitted, and debated in the time between this recording and whenever it happens to be heard. A few specific tests, in particular, are likely to matter more than the rest over the next several years. Larger spectroscopic surveys, covering wider areas of sky than the narrow, pointed observations that found JADES GSZ 140 and MOME Z14, will determine whether galaxies like them are rare, 1 in 1,000 outliers, or a genuinely common feature of cosmic dawn, a distinction that matters enormously for which explanation ultimately fits. Continued chemical analysis of additional early galaxies will show whether the oxygen enrichment problem is a one-off anomaly or a repeated pattern across many independently confirmed systems, the same kind of accumulating weight of evidence that eventually settled the dark matter question decades ago. And continued study of the little red dot population, sorting out what fraction are genuinely overmassive black holes versus some other, still unidentified phenomenon, will clarify how much of this entire story depends on a single unusual category of object, rather than several independent lines of evidence pointing the same direction. Each of these tests is already underway, in some form. Using data Webb is collecting on an ongoing basis, and the results, whichever direction they point, will narrow tonight's open question into something considerably more specific than it currently is. Rest now. Return, for a moment, to that first image, a mirror built from 18 gold-plated segments, folded small enough to survive a rocket launch, unfolding itself alone in the dark, nearly 1,000,000 miles from home. It was built to catch light that had been traveling since before the Earth existed, and it has done exactly that, more successfully than almost anyone allowed themselves to hope. What it found waiting in that ancient light was not the quiet, orderly beginning the models had predicted. It was something busier, brighter, and more difficult to explain. Galaxies assembling faster than gravity was supposed to allow. Chemistry building itself on a timeline that leaves little room to spare. Black holes growing at rates that strain the physics meant to contain them. None of this makes the universe less orderly. It makes it less finished, in the sense that matters here less like a settled record waiting patiently to be read, and more like a record still being uncovered, one photon at a time, by an instrument that keeps finding more than it was sent to find. That is not a small thing to sit with. The 300 million years this account has returned to again and again, the narrow window in which so much apparently had to happen, is not a flaw in the universe. It is simply the part of the record human instruments are only now sensitive enough to reach, and reaching it has revealed a chapter far more crowded and far more active than anyone had reason to expect. Scale is difficult to hold in mind, honestly, and it may help, here at the end, to try once more. 300 million years sounds, spoken aloud, like a very long time, and against a single human life, it is almost impossible to picture. Against the full span of cosmic history, it is closer to a held breath, roughly 2% of everything that has happened since the beginning, a sliver thin enough that the standard model expected to find almost nothing substantial within it. Instead, Webb found galaxies with structure, with mass, with chemistry complex enough to require an entire cycle of stellar birth and death already completed. Whatever the eventual explanation turns out to be, that basic fact will remain true. The universe used its opening sliver of existence more productively than anyone modeling it from a distance of 13 billion years had reason to expect. There is a kind of comfort available in that, if it is allowed to settle rather than resolved into anxiety about the unknown. The universe did not wait for anyone to understand it before it began building itself. It was already forming galaxies, already forging oxygen inside dying stars, already feeding its first black holes, in the deep, dark quiet of a cosmos with no eyes yet anywhere to see it happening. Understanding arrived much, much later, an almost unimaginably long stretch of cosmic time after the fact, carried by creatures made, eventually, from the same recycled stellar material this account has traced back to its origin. The oxygen in every breath taken tonight was manufactured inside a star that lived and died long before the sun existed. The uncertainty Webb has uncovered does not change that lineage. It only adds more detail to how it happened, how quickly, and how much of the process still remains only partly understood. Consider, too, what the word impossible has actually meant throughout this account. Not impossible in the sense of contradicting the laws of physics. Nothing observed breaks a single confirmed physical law. Impossible only in the narrower, more human sense of exceeding what a particular set of models, built by particular people, working with the particular data available before 2022, had predicted was likely. That distinction matters, because it reframes the entire mystery not as a crack in reality itself, but as a gap between reality and the current best human description of it, a gap that has opened before in different corners of physics, and as always, eventually, narrowed. Sometimes it narrows because the old model gets revised at the edges, the way star formation efficiency may yet be revised here. Sometimes it narrows because something new and unexpected gets discovered hiding underneath the anomaly, the way dark matter was eventually found hiding underneath Vera Rubin's rotation curves. And sometimes, rarely, it narrows because the model itself needed replacing with something deeper, the way Newton's gravity eventually gave way to Einstein's. Nobody yet knows which kind of narrowing is coming for the impossible early galaxies. But narrowing, in one form or another, is what tends to happen, given enough careful attention and enough time. Picture, for a moment, the researchers behind these findings, somewhere on the other side of the world from wherever this is being heard, working through exactly this uncertainty in real time. A postdoctoral researcher checking a spectrum for the third time before submitting a paper, wanting to be certain before putting a claim this strange into the permanent scientific record. A senior astronomer running one more version of a simulation, adjusting one more parameter, testing whether a slightly different assumption about early star formation might close the gap a little further. A graduate student, somewhere, staring at a little red dot in a data set at an hour much later than intended, wondering whether it might be the object that finally clarifies which explanation is correct. None of them know yet how this story ends. That, more than any single finding described in this account, is the truest picture of what doing science at the edge of the known record actually looks like, not a moment of discovery followed by tidy resolution, but a long, careful, collective process of checking, rechecking, and slowly narrowing the space of what could still be true. Picture the whole procession of it, laid out end to end. Hydrogen and helium gathered slowly by gravity out of the smooth, faint ripples left over from the universe's first fraction of a second. The first stars, igniting somewhere in the dark, burning hotter and dying faster than any star born since. Their deaths, scattering the first traces of oxygen and carbon out into the surrounding gas. A second generation of stars, gathering from that enriched material, forming the first true galaxies bright enough, it now appears, to be visible across more than 13 billion years of intervening space, caught at last by a mirror built specifically to catch them. And now, this very telling of it, spoken into a quiet room somewhere on a small rocky planet that would not exist for another 9 billion years after that first light left its source. Each link in that chain took unimaginable stretches of time to complete. Together, they add up to the entire span of everything that has ever happened. Somewhere above, tonight, that same 6-meter mirror sits in cold, permanent shadow, patiently gathering light that is, in every meaningful sense, older than almost anything else that will ever be observed. It does not know it has caused a controversy. It does not know its findings remain unresolved, debated in journals and conference halls by people who have not yet agreed on what they mean. It simply keeps looking, the way it was built to, adding one more sliver of ancient light to a record that is still slowly, patiently being written. Let that be enough for tonight. Not an answer, but the shape of a question still being carefully asked by careful people, using the best instrument ever built for the purpose, pointed at a sky old enough to hold almost every beginning there has ever been. Rest now. The universe has kept its secrets this long. It can keep them a little longer, until morning, until the next data release, until whichever careful hands take up the question next.